Geometric series, which is the focus of section 9.2, builds upon what we learned in section 9.1. So you may recall from section 9.1 that a geometric sequence takes the form S sub n equals a times r to the n, where n goes from, we're going to start at 0, 1, 2, 3, so on and so forth. So if we plug in various values of n, like n equals 0, we get a times r to the 0, which is just 1. I'm sorry, just a. If we plug in 1 for n, we get a times r. If we plug 2 in for n, we get ar squared, and so on and so forth. The first term is a, and then the quantity r is referred to as the common ratio. It's the quantity that we're always multiplying by to get from one term in the sequence to another. So a couple examples. 1/2 times 1/4 times 1/8, I'm sorry, 1/2, comma 1/4, comma 1/8, comma 1/16, so on and so forth. Now it's pretty clear here that to get from 1/2 to 1/4, I'm multiplying by a half. When I multiply 1/4 times a half, I get 1/8. When I multiply 1/8 times a half, I get 1/16, and so on. So in this case, the first term is 1/2, and the common ratio is 1/2 as well. S sub n is 3, 6, 12, 24, 48, 96. So I multiply 3 by 2 to get 6, 6 by 2 to get 12, 12 by 2 to get 24, and so on and so forth. So here the first term is equal to 3, and the quantity I'm always multiplying by, the common ratio, is 2. Now here's one that flips back and forth with positive and negative signs. What do I multiply 5 by to get minus 5/2? Well, it's minus a half. If I multiply minus a half times minus 5/2, I get 5/4. If I multiply 5/4 by minus 5/2, oh boy, I messed that up. What do I multiply 5 by to get minus 5/2? It's minus a half. What do I multiply minus 5/2 by to get 5/4? I multiply by minus a half. If I multiply this by minus a half, I get minus 5/8. If I multiply this by minus a half, I get 5/16, and so on and so forth. So in this case, a is 5, and the common ratio is minus a half. Another example, 1, 1/4, 1/9, 1/16, so on and so forth. Now I multiply 1 by 1/4 to get 1/4. If this is a geometric sequence, I would need to multiply 1/4 by 1/4 again to get the next term, but the next term is 1/9. Again, we always need to be multiplying by the same quantity, the common ratio, to get from one term to the next. So this is not geometric. Now the focus on section 9.2 is what happens when we take terms, individual terms, from a geometric sequence, and we add them. So we call such a thing a geometric sum. A finite geometric sum is the sum of a specified number of terms from a sequence. For example, here's a geometric sequence, 1/2, 1/4, 1/8, 1/16, 1/32, so on. It's consisting of the first 5 terms from this sequence, but now we're adding them together. It's not too hard to show that if you get a common denominator, you get 31/32. If we were to add the next term, which would be 1/64, we could show that the sum is 63/64, and what we're interested in is what happens when we add more and more terms from a geometric sequence. So again, a geometric sum is what you get when you add terms from a geometric sequence. So there's a nice way to simplify the formula, and here's what we're going to do. We're looking for a way of adding together very quickly a specified number of terms, be it 5 terms, 8 terms, 10 terms, 100 terms from a geometric sum. So we're going to let S sub capital N denote a plus ar squared plus ar to the third plus dot 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 up to AR to the n. This is the sum of the first n plus 1 terms from the geometric sequence A, AR, AR squared, and so on and so forth. Now, with a little algebra, we can actually determine a formula for S sub n. Let's take S sub n and subtract from it R times S sub n. So R times S sub n would be R times every term here, so it would be AR plus R times AR, which is AR squared, plus AR squared times R, which is AR to the third, and so on. Now, think about what would happen if we take this and we subtract this. Notice how if we take AR and subtract AR, we get them to cancel. If we take AR squared and subtract, the AR squareds are going to cancel. The AR to the third is going to cancel with that AR to the third. So if we take this and if we substitute R times S sub n, every term is going to cancel except the A and the minus A times R to the n plus 1. And so that leaves us with this. Now what we can do is we can factor S sub n out on the left side and then divide by 1 minus R, so that gives us S sub n equals A times 1 minus R to the n plus 1 over 1 minus R. This is a very convenient formula because this allows us to quickly add together any number of terms from a geometric sum, provided we know the first term and the common ratio. So here's an example. 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32. So we know that A is a half. We know that our common ratio is a half. And we know that n plus 1 is the number of terms that we're adding together here, which is 5. So let's use our formula. S sub 4, which is the sum of the first 5 terms, that's this quantity here, is the first term 1/2 times 1 minus 1/2 to the 5th, because n plus 1 is 5, over 1 minus R, which is 1 minus a half. And this is going to simplify nicely because this half is going to cancel with the remaining 1/2 in the bottom, and if we take 1 minus 1/32, which is what this would be, we would have 31 over 32. And this agrees with what we had above. Another example. 3 plus 6 plus 12 plus 24 plus 46 plus 96. I'm sorry, this should be a 48 plus 96. So in this case, A is 3, R is a half, and n plus 1 is 1, 2, 3, 4, 5, 6. So this adds up to be A, which is 3, times 1 minus 1/2 to the 6 over 1 minus 1/2. Now we could simplify this, calculate this, we won't do that. Another example. 5 minus 5/2 plus 5/4 minus 5/8, and so on and so forth, up through 5/32. Now we saw from above that these are, the individual terms come from a geometric sequence. In this case, A is 5, R is minus a half, and n plus 1 is equal to 1, 2, 3, 4, 5, 6. So S sub 5, which is the sum of the first 6 terms, would be A times 1 minus the quantity minus 1/2 to the 6th, all over 1 minus R, which is 1 minus a minus 1/2, or 1 plus a half. And we can simplify this and evaluate it quite nicely. When we add together many terms, it's convenient to use sigma notation. So the sum from n equals 1 to capital N of any sequence S sub n, we start at the index 1, S1, we move to the next index S2, and we keep adding terms together up through S sub capital N. You saw this notation in Calculus 1 in your discussion of Riemann sums. Now for the finite geometric sum, what we do is we start at n equals 0. So n equals 0 to capital N. We plug in n equals 0 here, so we would have a times 1. If n is 1, we have a times r, and so on and so forth. So this is the sigma notation for S sub n on the previous page, and we know from our geometric sum formula that this simplifies quite nicely. So for example, the sum from n equals 0 to n equals 20. This would be pretty hard to add by hand, but if we write this down, if n is 0, we'd get 1. 1/4 to the 0 is 1, plus 1/4. If n is 1, we get 1/4. If n is 2, we get 1 over 4 squared, which is 16, up through 1 over 4 to the 20th, whose value I'm not going to compute because it's going to be so small. However, if we use our geometric sum formula from above, this simplifies to be the first term, which is 1, times 1 minus r. R in this case is 1/4, to the 21st, because n is equal to 20, n plus 1 is equal to 21, over 1 minus 1/4. We won't evaluate this. Now what's interesting to note is that if we added, let's say, 60 terms, this would be 1/4 to the 60th power. And that's going to be pretty small. If we added from 0 equals n equals 0 up to 1,000, this would be 1/4 to the 1,000th power, which would be even smaller still. We know what happens as n gets larger and larger. So a geometric series is what happens when we let this upper end point get larger and larger. So instead of stopping at 1/4 to the 20th or something like that, we keep adding together. So the infinite series from n equals 0 to infinity of 1 over 2 to the n is what we get when we plug in 0, 1, 2, 3, 4, and keep adding and adding and adding. 1 plus a half plus a quarter plus an eighth plus 1/16 plus 1/32, and so on. Now let's recall that capital S sub n is given by this. And if r is between 1 and -1, we saw from our previous video that this has to go to 0. So if we take the limit as capital N goes to infinity of this, and if r is between -1 and 1, we know that this goes to 0. That means then that our geometric series, the series from n equals 0 to infinity, a times r to the n, it will add up to be, or converge to, a over 1 minus r if r is between -1 and 1, and it will diverge otherwise. So take a look at this formula, and if r is between -1 and 1, we know that this goes to 0. So as we add more and more terms together, we get something that looks more and more like a over 1 minus r. This is what's known as the geometric series formula. Let's take a look at some examples. The series from n equals 0 to infinity, 1/4 to the n. So this would be 1 plus 1/4 plus 1/16, and we would go on and on and on forever. This adds up to be, remember, a is 1, r is 1/4, so this adds up to be a over 1 minus r, which is 1 over 1 minus a quarter, and 1 minus a quarter is 3/4. 1 over 3/4 is 4/3. The sum from n equals 0 to infinity, 3 to the n over 2 to the n. When n is 0, we would get 3 to the 0 over 2 to the 0, which is 1. If n is 1, we would get 3 halves If n is 2, we would get 9 over 4, and so on and so forth. In this case, a is 1, and r is 3 halves, because I'm multiplying 1 by 3 halves to get 3 halves. I multiply 3 halves by 3 halves to get 9 fourths, and so on. In this situation, r is not between -1 and 1, so we say that this series diverges. And it's pretty clear in this case that we're adding together terms that are getting larger and larger and larger, so this adds up to be infinite, so to speak. Another example, n equals 0 to infinity, the summation of 4 times 3/5 to the n. If we write down the terms, if n is 0, we get 4 times 1, which is 4. When n is 1, we get 4 times 3/5. When n is 2, we get 4 times 3/5 squared, and so on and so forth. In this situation, a is 4, r is 3 halves, which is between, which is between 1 and -1. So this infinite geometric series adds up to be a over 1 minus 3/5, which is 4 over 2/5. Invert and multiply, that's 20 over 2, which is equal to 10. Next example, the sum from n equals 0 to infinity, 1 over n squared plus 1. If n is 0, we get 1. If n is 1, we get a half. If n is 2, we get 1 over 4 plus 1, which is 1/5, and so on and so forth. Now, in this case, the first term is 1, but there is no common ratio. I multiply 1 by a half to get a half. I would therefore need to multiply 1/2 by a half again to get the next term if this was a geometric series. But if I multiply 1/2 times a half, I get 1/4, which is not 1/5. So this is not geometric. So our formula does not apply. We can't determine what it is. The series from n equals 1 to infinity of 4 over 2 to the n. Notice that I'm starting at not 0, but at 1 this time. So let's write down the first few terms. If n is 1, I get 4 over 2, which is 2. If n is 2, I get 4 over 4, which is 1. If n is 3, I get 4 over 8. If n is 4, I get 4 over 16, and so on and so forth. A is equal to 2, and r is equal to 1/2, because I'm multiplying each term by 1/2 to get the next term. 1/2 is certainly between -1 and 1, so this adds up to be a 1 over 1 minus r, which is 4. Now, some geometric series have variables, and this is really the ultimate goal of the discussion in the next few weeks, is to look at infinite series that involve variables. So the series from n equals infinity, 0 to infinity, x over 3 to the n. Let's write down the first few terms. If n is 0, we get 1. If n is 1, we get x over 3 to the first. If n is 2, we get x over 3 squared. If n is 3, we get x over 3 to the third, and so on. So, what's a? It's 1. R in this case is x over 3. So the geometric series formula says that this will add up to be a which is 1, over 1 minus r. 1 over 1 minus x over 3. And if you multiply everything in the top and the bottom by 3, you get 3 over 3 minus x. But we have to be careful here, because this is only valid. These guys only add up to be 3 over 3 minus x if our r value is between -1 and 1. So in other words, -1 has to be less than x over 3, which has to be less than 1. If we multiply through to get x in the middle, this says that -3 has to be less than x has to be less than 3. And this is what we call the domain of convergence. The domain of convergence. So if our infinite geometric series involves a variable, it converges, but it converges dependent upon what the value of the variable is. If we change this to be x over 5, it's pretty clear that x would have to be between -5 and 5. Okay, so here's what I'd like for you to do in preparation for the next class. Section 9.2, exercises 11, 15, 16, 18, and 19. I'll see you then.